We have boiling point elevation. It's a colligative property like everything we're talking about within this chapter. It doesn't depend on the identity of the solute. What you're dissolving does not govern what boiling point elevation will be. It's just how many particles there are. The solvent is where you get the number for this constant that you're using for boiling point elevation. Every solvent has its own. And you might have to use the Van't Hoff Factor I. So overall, here's our equation, and now we're going to do a little puzzle with it. We have crude oil pumped out of the ground, maybe accompanied by saline formation water. If the boiling point of a sample of formation water is 2.3 degrees Celsius above the normal boiling point. Okay, they just told us something. They told us what delta TB is, that it's 2.3 degrees Celsius. Then it asks, what is the molality of dissolved particles in the sample? You'll notice this wording, that the molality of the dissolved particles. They aren't asking whether they're molecular or whether they're ionic. And so what we're going to end up doing, since there's probably a great deal of different ones in there, is we'll take our formula and we will simplify it to simply be KB and M, because we're not looking for anything specific. We're just looking for the overall molality of all the different types of particles in it. So I is not going to come into the problem at all this time. I need to know what M is. I'll just rearrange this formula and say that it's M equals delta TB over K sub B. I already know this number, 2.3 degrees Celsius, and I needed to have the KB of water. So I can go look that up. That's a very common one to go find. And what KB is for water is 0.52 degrees Celsius per molal. You can see the degrees Celsius are going to cancel, and the molality is going to get popped up to the top. I get 4.4 molal. I still don't know what they're made out of, but I do know the grand total is this molality. This one is about freezing point depression. Again, it's a colligative property. Again, it doesn't depend on what the solute is. It's the solvent that is the source of the K sub F. And you might have to use the Van't Hoff factor depending on what's going on. So for number 11, we're going to be using this formula. And it says the freezing point of a 1.2 molar solution of magnesium sulfate is 2.31 degrees Celsius below the freezing point of pure water. If the density of the solution is this, what's the value of I? If I'm asking for what is I will do a little algebraic manipulation and say that it's a delta TF over K sub F and the molality. They have already given me delta TF because they told me it was 2.31 degrees below the normal amount. They also told me that this is water, so I can go look it up. I find out it's 1.86 degrees Celsius per molal. Then there's the molality. They didn't give me molality. They gave me 1.12 molar, and that's not the right units. You will notice they've given me something in here. They said the density of the solution. So what I'm going to do is I'm going to remember what the definition is of molality and write it that way. This would be 1.12 moles of solute per liter of solution. Definition of molality, this top part's fine. The bottom part, not so much. They have not told me how much solution I have. It shouldn't matter. I'm going to make an assumption that I have 1 liter of solution. If I have 1 liter of solution, then I can go ahead and turn that into milliliters and then use that density, 1.126 grams per milliliter. So the milliliters will cancel, the liters will cancel. And we will end up saying that we had 1,126 grams of solution. But what I really need is kilograms of solvent. They told me how many moles were in it. I have 1.12 moles of magnesium sulfate. So I can go figure out what the molar mass of this is. I'll find out it's 120.37 grams per mole. Cancel the moles. And I find out that the solute in here weighs 135 grams. If I subtract that, I'm subtracting the solute from the solution. The only thing that is going to be left is the solvent. I get 991 grams of solvent. So that is 0.991 kilograms. I have the fact that I need this in molality. I already know it was 1.12 moles of solute, and now I know it was 0.991 kilograms of solvent. And when I run that through my calculator, I find out that I get 1.13 molality. You will find that if you are doing aqueous solutions where water is your solvent, that the numbers for molarity and molality are not much different. But if you are working with other solvents, there will be a big difference between molarities and molalities. This one, it just was in the last sig fig. Okay, so let's finish the problem. I is 2.31 degrees Celsius, 1.86 degrees Celsius per molality, and then I have 1.13 molality. I'm going to end up canceling all the units, which is good because I should be a pure number. I get 1.099, and I can't keep all those sig figs. I can only keep 3, and I end up rounding this to 1.10 for the value of I.